We have just discussed last time that when we have this system of equation, there are three possibilities, that they have the reference solution, only one solution, they can have many solutions, they can have no solution. Then we classified this one in two things. There's consistent and inconsistent. Consistent, when we say, that means I have one solution, I have many solutions, infinite many solutions. Inconsistent means there is no solution. So now today we are going to discuss, we'll take the examples and we will find that when the system will have only one solution, many solution, or no solution. So I have taken the example here. Just before doing the example, I want to give you a little idea about that one. We have seen it. We're having here this equation y as 0x, 0y, 0z. If the right hand side is 0, that means one of the row is 0, and the system, if there are three unknowns and they will remain two equations, we have many solutions. If instead of this we are having a 0x plus 0y plus 0z equal to, say, a minus 2. So this means 0 is equal to a minus 2. Now a is a real number. Now there come the possibilities. Then it can have no solution, have many solutions. If this side is equal to 0, then we get here this, like this one, 0 is equal to 0. And if this side is not equal to 0, this means that there will be no solution, because then 0 is not equal to some number. So here we can see it here. This will be happening when a is equal to 2. Then we say there's many solutions. Many solutions. Or we say the system is consistent. Sorry for that. Yeah. When a is not equal to 2, that means we're having here 0, a equal to 1. 0 is not equal to minus 1. A equal to 3. 0 is not equal to 1. So it means there will be no solution. So that from the last row, any row which is right hand side, left hand side is 0, and right hand side is non-zero. So we will going to look on that one. This is the idea we are going to apply in this example. So solution of this example is same as we discussed Gauss elimination method and Gauss-Jordan method. In the last lecture we have a row echelon form or reduced row echelon form. We don't have mentioned anything here, which method we are going to use. So when we develop our solution, according to that one, we're going to see which method we are going to take it. But always when we start from the augmented matrix form. So our solution is, we always write our A and our B. What's our A? Our A is the matrix of coefficients. What's our B? B is matrix of constant. And that's my augmented matrix. So I'm having here the data 2, 3, 1, and this is minus 1. I'm here 1, 2, 1. We're having 0. So get here 3y a square, sorry, not y. The value of coefficient of y, that's equal to 1. And then we're having a square minus 6. And this is our matrix of constant on the left and the right hand side. We get here a minus 3. So I'm having here, this has my row 1, this is my row 2, and this is my row 3. And again, we are going to solve by using the elementary row operation. Number 1, we can interchange two rows. Number 2, we can multiply row with any real number. Number 3, we can add multiple of our row to another, and this way we reduce, make the reduction, make the elimination. So we can see it here. The first value we want to bring here 1. So we can interchange two rows. That's we just change here R1 and R2, and we write our new system of equations. In this case, we having this first value as 1, and we can have here, we rewrite this one and making this a row operation that, let's see, we are going to have this my equivalence of this one, AB. And I'm having here 1, 2, 1, and we have here 0. Now my second row becomes 2, 3, 1, and minus 1. And my third equation is 3, 1, a square minus 6. And we're having a minus 6. This new set of new augmented matrix form. Now this is my new row 1, this is my new row 2, It's my row 3. Now next step is that we want to use this A and want to eliminate this 2 and 3. We want to make it 0. So to make it 0, we are going to use here the row operations, and my row operation will be I multiply first row by -2 and add to the second row. That will make this value 0. Next row operation will be add to -3, add to this one, -3 R1 plus R3. So in this way, I'm going to make this value 0. Now let us see, always as I told you, we just write them separately to obtain the accuracy of a result. So I have some space here and use this, I use this space and I do this work here. I multiply first row by -2, I get -2, -4, -2 and 0. And at the second row, I get here 2, 3, 1 and -1. Add it. I get here 0, I get here -1, I get here -1, I get here -1. So I rewrite this one. So I'm having here my first row, that's not changing. I'm using this one. I have here 1, 2, 1 and 0. Now we have done already many examples and we know then this here I want to bring -1. So what I do, I multiply this row by -1. So here I can write this one that I multiply here by -1. So what I'll get? I'll get here 0, 1, 1 and 1. Now we're going to multiply here by -3 and add to this one. I multiply -3. I get here the value as -3, -6, -3 and 0. And we add the last row. We get here 3, 1, a square -6 and a -3. We add it. We get here 0. We get here -5. We get a square -9. We get here a -3. So we write it here. We get here 0, -5. I get here a square -9. I get here a -3. Now my next step is that I am going to make this one 0 because I have to find the values of a, which will give me infinitely many solutions, no solution, exactly one solution. And that is in my third row. So I'm dealing with the third row. So I just focus on this one. So multiply here by 5, R1, R2 plus R3. So multiply by 5, I'll get here 0, 5, 5 and 5. And I add my last row, that's 0, -5, a square -9 and a -3. We add it, we get here 0, we get here 0, we get here a square -4, and get here a plus 2. So I am having here the equation in this case. So here I can write, this is equivalent to, the first row remain the same, this is 1, 2, 1 and 0. And then I'm having here 0, 1, 1 and 1. And I have my last row that's equal to 0, the new one, 0. I get here a square -4 and a plus 2. The row operation I made, that was minus plus 5 times R2 plus R3. Now I am having my last row. I will focus on my last row and I will take my conclusions from there. So if you can write in the equation form, or even if you don't want to write an equation form, you can see here the last row. Last row we are having here, last row, that's our R3. We rewrite this one, we get here 0, 0. We can just make the fraction. We're having a minus 2, a plus 2, and here we're having a plus 2. Now my focus is here, and this is my whole matrix, this is my last row, this is my R3. Now this will give me the idea that when it's having many solution, no solution, and one solution, we can see it here. If we are having here, this row is 0. This is our leading entry, this is our leading entry. There are two leading entry, and one entry will be free entry. There will be many solutions. When these both are 0, we can see here number 1. If we take a is equal to 2, a is equal to minus 2. So this will be 0, this will be 0. What we'll get? We'll get here 0, 0, 0, and 0. So we say there are infinitely many solutions. many solution, and the system is consistent. When A is equal to -2, system is consistent, it has many solutions. Number 2, no solution. Number 2, we are having here the case of no solution. For no solution, we say this is 0 and this is not 0. We can say when it is 0, we take A is equal to 2, this becomes 0 and this becomes 4. So we say when we're having A is equal to 2, we can have here the last row. Our last row is 0, 0, 0, and here is 4. And we say here 0 is not equal to 4. This implies there is no solution, because this is not an equation. There is no solution. And here, when there is no solution, we say the system is inconsistent in this case. When we take A equal to 2, the system is inconsistent. Number 3, we want to see when it's having exactly one solution. So we're having only 2 possibilities. A can be 2 and A can be -2. When A can be 2, we're having this is 0 and this is 4, no solution. A can be -2, this is 0, this is minus solution. So we say if A is any real number except -2 and 2, there will be only one solution. There will be only one solution. We say is unique solution. Only one solution, what we say? We say unique solution. If we want to see when the system is inconsistent, that means when system don't have any solution, we can write immediately when A is equal to -2, the system is inconsistent. When you say the system is consistent, then you say it has at least one solution. So it having at least one solution means it can have many solutions or only one solution. So it will be A is equal to -2 or A is other than 2. So that having consistent have one solution. When it is -2, it will have many solutions, and when it's other than 2, it will having only -2 and 2 is having unique solution. We take another example and we try to see how the system will have unique solution, many solutions, and an infinite number of solutions. Or we say we can also say it when it's consistent as inconsistent. So we're having different situation from the last example. We have lambda coming in the first row, equation also, and so here we are going to take it and we see that how it's going to. And also we're having here, this is lambda is coming on the left hand side, right hand side, and left hand side. So again, we always start with the argument matrix form. So we write the argument matrix. A is a matrix of coefficient and B is a matrix of constant, and we write it. We are having here, this one is 3, 0, lambda, and right hand side we're having the constant is 2, and the coefficient here is 3, 3, and 4, and here the value is 4, and the last row we get here 0, 1, 2, and lambda. So these are our 3 equations which we are going to solve it and to get the result. Now here, as I told you, when we say reduced row echelon form or row echelon form, then our row must start from 1. But when not taking this row echelon form or row echelon form, we just take general form of the Gauss-Jordan or Gauss elimination, then we can retain this value as any number, 3, 4, 5, 6, whatever the number is. But reduced row echelon form or row echelon form must be starting value, leading entry, that is 1. But here we are not given the instruction that which method we use, so we are independent. We keep this 3 there because we can see immediately that the next row is 3 and this can be easily turned to be 0. So here we can just multiply -1, add to this one. It's minus R1 plus R2. So I get here new matrix. My new matrix, the first row remains the same. This is 0, 3, 0, lambda. And we're having here 2. We make the row operation, multiply by minus, get here -3, 0, minus lambda, and we get here -2. And we add the second row. The second row is 3, 3, 3, 4, 3, 3, 3, 4, and we're having here 4 also. So we add this one. Our new row will be 0, 3, we're having 4 minus lambda, we get here 2. So I can write here, this is my 0, 3, 4 minus lambda, and 2. And here there is already 0. So we can write it. So we get here 0, we get here 1, we get here 2, and we get here lambda. Now we can see we're having lambda in the second row, and we're having the lambda in the last row, and we are going to simplify this one. So to do that one, we just multiply here by 3 minus 3 and add this R3 to that one. So we R2 minus 3 R3. So we get here my new equation that's equal to 3, 0, lambda. And we get here 2. My second equation, I will keep it like this, 0, 3, 4 minus lambda and 2, and multiply minus 3. I get 0, minus 3, minus 6, minus 3 lambda. And I have in the second row this 0, 3, 4 minus lambda and 2. We add this one. We get here 0, 0. We are having here minus lambda, minus 2. And we are having here 2 minus 3 lambda. So this is my equation. I'll get, I would like to change this one, the sign to plus. So I multiply here by minus 1. I can write this one 0, 0, lambda plus 2, and I get here 3 lambda minus 2. So this is my reduction form, and as we are having in the last row, the matters which is containing lambda, and that will give us the idea that it's having here one solution or many solution, and we having the no solution. Now in this case, I would like to write the system form. The last example, I like the matrix form and then discuss that one, the solutions. You write the equation form, we having 3x, then we having plus lambda z is equal to 2. Now my second equation is 3 plus 4 minus lambda z is equal to 2. And my third equation is lambda plus 2 into z is equal to 3 lambda minus 2. This is my equation 1. This is my equation 2. This is my equation 3. We focus on the last equation. We want to see here then when it's having a unique solution. Unique solution is when this is not 0 and this is not 0, then we get the unique solution. When this is 0, this is not 0, no solution. When this is 0 and this is 0, then we say it's having only many solutions. So number 1, we take here, number 1, unique solution. So for a unique solution, we can see what the value of lambda must be. So we say here lambda is not equal to 0, not equal to minus 2. Why? Because lambda equal to, then this will be equal to 0. Lambda can be any number. Lambda can be any number. It can be 0, but there will be a unique solution. The only condition is lambda is not equal to minus 2. So this must not be 0. This must not be 0. This must be the leading entry. We can divide this one by lambda plus 2. Then lambda plus 2 come in the denominator. And we can write here z is equal to 3 lambda minus 2 and lambda plus 2. So here we can see lambda is never equal to 2 because lambda equal to minus 2 it become infinity. So we have lambda never equal to minus. So this is unique solution. Then we are going to look for the no solution. For no solution, we know that when our left hand side this is 0 and this is non-zero. So we can see a lambda equal to minus 2. What lambda equal to minus 2 will give me this 0 times z is equal to lambda equal to minus 2. We get minus 6 minus 2. So 0 is equal to minus 8. But we know that 0 is not equal to minus 8. So we say there is no solution. Then case 3 is when it's having infinitely many solution. For infinitely many solution, we must have the last row equal to row of zeros. But last rows can't be row of zeros. When we take lambda equal to minus 2, this will be 0, but this will be not equal to 0. When we take lambda equal to, we make this one 0, that we take the value of lambda 2 by 3, then this 0 and this will be not equal to, they will have a solution. So we say does not exist. There is no solution which exists for infinitely many solutions. So in this example again we are having the same idea that we want to see when the system is consistent. The system is consistent when it is having at least one solution. This means it can have one solution or infinitely many solutions. Again, as before, we always write our system in the argument matrix form. Here I use capital D for the constant because small d is being used here. So it's my coefficient, the coefficients of the matrix, and here are the constants a, b, and c. And we want to get the relationship between a, b, and c such that we must get the condition mean a relationship between a, b, and c that satisfies the system of equation to be consistent. So we just use the elementary row operations and we solve it, and we see that what the result we're going to get here. So we write here again our operation. So we're having here 1 to make this one 0 and this one 0, and our row operations to make this one 0, that multiply first row by -1, add to second row, multiply first row by -2, we have minus R1 plus R2, and then to make this one 0, we have minus 2 R1 plus R3. So we check our row operations and we see how the things are going. We multiply by 1, we get here -1, we get -1, we get -2, we get here minus a. And then we having here 1, 0, 1, and b. We add it, we get here 0, we get here -1, we get -2, we get minus a plus b. So we are having first row without any change, we're having 1, 1, we're having here 2, and here I get my a. The second row, making the row operations, I will get here 0, I get -1, I get -2, I get here minus a plus b. The next is we multiply -2 and add R3, -2, we get -2, we get -2, we get here -4, we get here -2a. My R3 is 2, 1, 3, and I have c. So I just add it, I get here 0, I get -1, we get here -1, we get c minus 2a. So I just rewrite this one, I'll get here 0, I get here -1, I get here -1, I get here c minus 2a. So here is also there is small mistake. We're not getting 2, we get here -1. So I am having here -1. So this is my new R2. We look on this new R2 and R3, you can see immediately, and multiply -1 and add to this one, this will be 0, this will be 0. So we do it, we have minus R2 plus R3. So multiply -1, we get here 1, 0, 1, 1, and we get here b minus b plus a, because this become plus and this become minus. I will write here a minus b, that's better. We get here a minus b. So my last row is 0, -1, -1, and here I get here c minus 2a. We add this one. Adding this, I'll get here 0, I get here 0, I get here 0. I am having here c plus minus a and minus 2a and minus a. That give me here minus a, and then here is minus b. Again, look here. I have a plus a and minus 2. Adding this one, we get minus a, and this is c is plus and b is minus. So my last row will be, I'm going to have the change. I rewrite this one. I get here, the first row is 1, 1, 2, and a. The second row is 0, -1, -1, minus a, and plus b. And my third row, I'm going to get here this 0, 0, 0, and I'm having here c minus a minus b. I want to look at the conditions when it's having consistent. We know that this is 0. We have two leading entries, and there's no entry here, 0 row. This is our form that if this is 0, this will be consistent. We have many solutions. Many solutions mean consistent. I said only one solution is consistent. I say we have at least one solution. So we say system is consistent. That give me the condition of consistency. System is consistent. Consistent if we get here c minus b, c minus a minus b equal to 0. They give me the condition c is equal to a plus b, and this is my solution. So there are many examples in many exercises given in all the books. You can solve from the exercises, because exercise is very important. These videos will help you to understand it, that how you are to have to perform it. You can repeat these videos and try to, if it's not clear, to make yourself clear, and then do more exercises to understand it perfectly.